Well, hello, ladies and gentlemen. This is ME 2134, Introduction to Thermodynamics. So I'm Dr. Matthew Rice. I'm going to be your instructor for the semester. So we're going to spend the day going over introductory topics for the course, administrative stuff. So topics, administrative, stuff, the syllabus, the procedure from when you have to fill out a request for excused absence, in other words, getting excused from submitting homework or doing exams. We're going to go over basic course administration. And then we're going to go over, for today, motivation for the course. Motivation for the course. Why are you taking thermodynamics? What's different about what you've done, what you're going to be doing here, as opposed to what you've done in basic physics? What's the motivation for doing thermodynamics? So those are the two topics for today. We're going to make kind of a short lecture, given that we have 2 more lectures this week. So let's go over the syllabus here. So let's go to the syllabus. So this is on Canvas under administration. You'll find the syllabus, and we'll talk about the request for absence form in just a moment. So Thermodynamics 2134, fall 2020. I'm Dr. Matthew Rice. My office is 114I Randolph. So if you go to the very back of the CAD lab, my office will be off to your left. Office hours, I think Monday, Tuesday, Wednesday, given those are the days that we have lecture, from 4:30 to 6, actually 4:30 to 6:30, so that's 2 hours. I presume those of you that have part-time jobs, hopefully that will be okay. Most of you should be around by 4:30, or at least not going to work till probably around 6 if you have a part-time job. So I think 2 hours, 3 days a week is going to be sufficient. Textbooks, Fundamentals of Engineering Thermodynamics, 8th edition. That's a standard textbook for the course. However, as far as I'm concerned, you can also purchase the notes for the course, Thermodynamics, a short undergraduate introduction. Short undergraduate introduction. Copies of these are available outside my office. There's a pile of them on the metal shelves. They are $16 a piece, so they're very affordable, and they include all the material you will need for doing the course. They are the course notes, and they also include property tables. You'll be learning about this starting in a day or so, determining properties of substance. So everything you need in the course will be provided in the notes as well as the main text. The notes, I think, is a lot more compact and goes at the material in a similar way as the lecture. Let's go over the grading here. 2 tests, 2 midterms, 20% each, 40% for the course. And then we have homework, which is 25% for the homework, 5% for lecture quizzes. We will occasionally have post-lecture quizzes that will be open the entire day on Canvas for submission. We'll figure out how we want to do these quizzes when the time comes. Either they will involve printing some kind of a worksheet out and filling it out and then scanning it, or it will involve quiz questions on Canvas. Maybe it'll be a mixture of the two. And then, of course, we have the final, 30%, remaining 30% for the course. So 40% for the midterms, 30% for the final, and 30% for homework and quizzes. The grade distribution, very similar to what you've seen in other courses. Above a 90 is some kind of an A, between a 90 and an 80 is some kind of B, on and on and on. So this is very standard grading distribution. So the topics here, let's go over the topics. Well, You're going to be analyzing thermodynamic systems and determining properties for the systems. There are also relationships that relate properties. And what I mean by properties are things like temperature, pressure, volume, things that describe a system. We'll talk about systems as well here very soon. So we're going to be learning about properties and how they're related. We're going to be applying open and closed system conservation equations for mass, energy, and entropy. So I think you all know what mass is, obviously, what energy is. You probably don't know what entropy is, even though you've heard of it. But we're going to be looking at how mass, energy, and entropy are conserved. There are conservation equations that relate changes in energy, entropy, mass to various other parameters. Okay, so we're going to learn about these conservation equations. We're going to be learning about work-producing devices, gasoline engines, diesel engines, jet engines. These devices are idealized by various cycles, the Otto cycle, the diesel cycle, the Brayton cycle. So we're going to be investigating work-producing devices, cyclic devices. And what you learn will be relatable to gasoline engines, diesel engines, jet engines, and that also includes power plants, the power plant across the street. So we're going to be learning about devices that produce work of various kinds. We're also going to be looking at conversion devices, nozzles, diffusers, throttles. These are devices that don't produce or consume any work. They simply convert different forms of energy. So we're going to be learning about conversion devices. We're also going to be looking into detail on various work-producing devices such as power plants. We're going to look at the various components inside power plants, what they do, how they enhance the efficiency of power plants. We're going to look at in detail on the devices within a gas turbine, a jet engine, and how each and every device works within the whole. So the class is going to start off typically looking at things in general, and then we're going to zoom down into the specifics as we delve deeper into each particular topic. There's a lot of material in this course, a lot of detail, and you are going to learn a lot in this course. We're also going to be learning about heating, ventilation, and air conditioning. If any of you are interested in things like humidity, relative humidity, absolute humidity, dew point, maybe these terms are known to you, or you're just in general interested in heating, ventilation, and air conditioning systems, we're going to go over HVAC systems and do some simple preliminary design on simple HVAC, heating, ventilation, and air conditioning devices. We're also going to look at refrigeration devices. These are work-consuming devices or power-consuming devices. They take energy and they move heat around. Typically, they'll move heat out of a cold system. Your refrigerator has a device at the very base which operates on a refrigeration cycle. It extracts heat out of your icebox or your refrigerator and dumps it into your room that contains your refrigerator. So we'll talk about refrigeration systems as well. So we're going to look at work-producing devices, and we're going to look at work-consuming devices. In this case, refrigeration devices. And then towards the end of the course, we're going to be looking at combustion as well. So we're going to look at combustion, in other words, furnaces, heat exchangers, that sort of thing. So we're going to be looking at chemical reactions. and see how energy is released when you oxidize or burn a fuel. So we're going to be looking at combustion, and that's towards the end of the course. So there is a lot in this course. I think that you will find that of all the courses you've taken at Virginia Tech so far, thermodynamics is probably going to be the most challenging, but you have the opportunity for learning the most interesting stuff. You will be able to analyze all sorts of devices that remain a mystery to the rest of mankind once you are done with thermodynamics course, okay? I think it's a very rewarding course. I think you will find it very rewarding. Let's go over some of the policies here. You've got some prerequisites. You should look over the list of prerequisites here and make sure that you are current, okay? Now, exams. So if you look on the very last page, I have a general list of topics per week. I don't have a detailed daily schedule, but I do have a weekly general schedule, and you'll see that the exams, the first exam and the second exam, the midterms are listed approximately a third of the way and 2/3 of the way through the course. So we have two exams. We'll go over the details on that when the time comes. We also have quizzes, and these will typically cover lecture material. So either after the lecture, usually after the lecture, I will allow you a day to complete and submit a quiz. The quiz may still be timed, but you can do it any time during the day. We'll go over the details on that when the time comes. So there will be quizzes. Homework again, we have homework. You learn thermodynamics by doing it, not just listening to me lecturing or reading it out of a textbook or your notes. You actually have to do it. You learn everything by being exposed to the concepts, seeing examples, and then doing the work yourself. So 25% or a quarter of your grade is based on the homework. So it's critical for you to get practice doing thermodynamics. Now, what happens if you, for whatever reason, cannot attend a lecture and therefore cannot do the quiz, or you cannot do the quiz on time, or you cannot attend a midterm or the final, and you need to get a reschedule, or you cannot submit a homework on time due to some sort of obligation? Well, we have a procedure for that. Let's go to the second item. The second item that is under administration in Canvas. This is your request for absence form. Let's go over how this works. So instead of you sending an email to me telling me about how you're going to be absent on a particular day and requesting what to do, we have a system here. You have this form called the Request for Excused Absence form, and it's for ME 2134. You must fill out this form and submit it to a web address, an email address, along with justificatory documentation. Let's go see how this form is actually arranged here. So if you are to miss a quiz or a homework assignment or a midterm or the final, and you have justification for doing so, I don't mean you slept in, I don't mean you don't want to do it or feel like you can't do it and you're panicking. I mean if you have a legitimate excuse. Legitimate excuses are, participation in an athletic event for Virginia Tech, participation in a conference or attendance of a conference that conflicts with your time for taking the course. It could also include illness, but the illness must include some kind of a note or documentation. I do allow for bereavement, including weddings. So if you have to attend a funeral, you must provide documentation on that, either an airline ticket or a copy of an obituary. If you're attending a wedding, I would like to see a copy of the wedding invitation attached. So I allow you to excuse yourself from coursework and the exams under restricted conditions without penalty. But you have to fill out this form and you have to submit it to an appropriate email. So you put your name, you put the date in which you're making the request for an absence, in other words, today's date, and then down here you check whether you're going to miss a lecture, i.e. a quiz, a homework, or an exam. Then below that you have the day in which you are expected to be absent, or days, plural. And then below that you have to write out the reason for your absence. Athletic event, if you're on a team. Design competition, if you're on a design team. Conference, funeral, wedding, illness. And all of them have to include some kind of supporting documentation. You should write down what the documentation is, and you should attach the documentation to your submission. So I would fill out the request for absence form, print out your documentation, scan them together as a single document, and then submit them to the following Yahoo account, me2134instructors@yahoo.com. Send your filled out request for absence form along with your documentation to that email. Once a week, I will process it, and I will get back to you on whether you have been approved or not for your request for absence. If it's a planned absence, i.e. a job interview, athletic events, something like that, I expect you to submit the request for absence 1 week ahead of time. If it's an unplanned absence, an illness, death in the family, all provided with some kind of documentation, then you need to submit a request for absence for the days that you missed no later than, what do I have here? I think I have a week after or something like that. Let's see. Yes, 1 week after the absence. So if it's a planned absence, you need to submit a request for absence form 1 week before you're going to be gone and miss the work. If it's an unplanned absence, typically an illness or something like that, or a death in the family, you need to submit a request for absence form no later than 1 week after the absence took place. Okay? Okay, so let's go back to the syllabus here. Oops. So if you miss exams, quizzes, homework, you have to submit a request for absence form so we have documentation. Okay? Grades we've already talked about. They're distributed between the quizzes, tests, homework, and the final. The honor system, you're all adults, you know about this. Just don't cheat. Make the work your own. Don't copy somebody else's work. Don't go to some website and copy it down. A lot of the homework assignments I'm going to give you are not going to be available on the internet. They will be my own or other faculties' custom homework problems, and that same thing goes for the exams. Same thing goes for the exams. So I wouldn't spend a lot of time on the internet looking for this stuff. Let's go over the course schedule. So again, 2 text. The required text is Moran and Shapiro's Fundamentals of Engineering Thermodynamics. If you can pick up an affordable copy, new or used, please do it. However, as far as I'm concerned, a copy of the course notes, which also includes all the property data, the technical data that you're going to need to do problems, all that's included in the course notes, is just fine with me. The course notes is very affordable, $16, and you can pick up a copy of the course notes outside my office. There is a pile of them on the metal shelves. Topics, tentative course schedule. This week we're going to start off with basic concepts and motivation. And then we're going to look at properties of pure substances. We're going to start the course off as easily as possible, starting with the basics. And we're going to look at properties of systems. What's the energy of a system? What's the enthalpy of a system? What's its pressure, temperature? So we're going to look at properties of pure substances. Okay? And then week 2, we're going to continue on with the same thing, wrap up pure substances, properties of. And then week 3, we're going to go into interactions, work, heat. We're going to define work and heat. I think you already know what work is from physics. We'll talk about heat. What is heat? Then we're going to move into the guts of the course, or begin the guts of the course by investigating the energy balance. Hopefully you've already been introduced to the energy balance in basic physics. Work is equal to the change in total mechanical energy. So work is equal to delta KE plus delta PE, kinetic and potential energy change. We'll talk a little bit more about that in just a moment. So we're going to move on to the energy balance, and then we're going to apply the energy balance to various kinds of systems and devices. You're going to learn about open and closed systems. Okay, there are different versions of the energy balance we're going to use depending on the device being analyzed. Then we have we're going to move on into the second law of thermodynamics, which is all about entropy and efficiency. That's where things start getting really interesting, when you get into entropy. For many of you, your brains are going to start curdling. Entropy is weird. You just have to accept it, get used to it, and one of these days you're going to wake up and it's going to make sense. Hopefully that will be this semester. You wake up and it will make sense. So we're going to move into the second law and entropy around the first exam. And then we're going to look at the entropy balance, conservation of entropy. Just like we look at conservation of energy, we're going to look at conservation of entropy. Entropy is a property just like pressure, just like temperature, just like energy. Entropy is a property. Okay, so we're going to look at the entropy balance and apply it to various systems. Then we're going to look at work-producing devices. Gasoline engines, diesel engines, jet engines, power plants. Okay, once we have the energy and the entropy balance, conservation of energy and entropy under our belt, we can move to serious analysis of somewhat complicated systems. Work-producing devices like engines and power plants. And then we'll take, after that's done, after we've looked in detail at work-producing devices like engines and power plants, we're going to move on to work-consuming devices like refrigerators. Refrigerators are not about producing power, they're about moving heat. Typically moving heat from a cold place to a hot place. Okay, we'll talk more about heat in a few days, okay? Actually in a few weeks. We'll talk more about heat in a few weeks. So once we've gone over refrigeration, we're going to go on to heating, ventilation, and air conditioning. Heating, ventilation, and air conditioning. That'll be fun. We can talk about how the AC system works in your air conditioning, for your apartment, for the building you work in, wherever, in your car. And then we'll talk about heating, ventilation, and air conditioning. How to condition air and extract out excess moisture. How to heat up air. How comfortable does the air feel to be in, depending on the humidity and other things, okay? So we're going to talk about HVAC, heating, ventilation, and air conditioning, okay? And then we're going to finish off the semester with chemical reactions and reacting systems. Up to the last 2 weeks of course, we're not going to look at combustion. We're not going to look at things burning. We're not going to look at chemical reactions. We'll save that for the last 2 weeks of the course, okay? Last 2 weeks of the course. Okay, so I think we've gone over enough of the material here. Basic material for the course. So let's go through, let's switch out of this. Switch out of this. And let's go over a motivation for the course. Why are we taking thermodynamics? Why are we taking thermodynamics? So what's the motivation here? Motivation. Let's go over the motivation. Motivation. What's the motivation for the course? Well, let me write down the energy balance, conservation of mechanical energy, as you learned it in your basic physics course. What you should have seen from physics is work is equal to the change in kinetic energy of a system plus the change in potential energy of the system. And remember, this delta here means change. It's the Greek letter delta, and it means change. Change. By the way, I haven't brought it up, but I have posted on Canvas under the miscellaneous folder. If you go to Canvas and under miscellaneous, you will see a list of Greek letters and what they are called. So for those of you that are a little bit rusty on your Greek letters, and we're going to be using a lot of Greek letters, I have posted a list of Greek letters and their names. So delta, or this triangle, refers to change. So this is the energy balance, if you like, from what you learned from physics. This is conservation of mechanical energy. Mechanical energy. Okay. Conservation of mechanical energy. You learned that from physics. You learned that from physics. Okay, now I am going to apply this energy balance here, conservation of mechanical energy, to a very simple situation. And I'm going to show you that this equation, although it's very useful for many systems, is not the end of the story. This equation, under certain conditions, is true, but is not the whole story. It's incomplete. It's incomplete. Okay, so let's say I have the following system. I have a table. So here's our table. And on this table is an object, okay? Maybe it's the eraser, okay? Maybe this is a tabletop and the eraser is on the top. So this is our table, and this is some sort of mass. I don't know, it might be my eraser. Might be my eraser, all right? So this mass has a velocity VEL1. VEL1, okay? Has a velocity VEL1. It also has a mass 1, or I'll call it just M. M for mass, okay? Now, originally, I'm going to call this state number 1. This is state number 1. This mass is moving along the top of this table. This mass has a velocity VEL1. And if I stick a thermometer on the table and the mass at state 1, or if you like, at time 1. Instead of thinking about state, let's think about it in terms of time. Time 1. If I stick a thermometer here and I measure the thermometer, I will get a temperature T1. Temperature T1. So this table mass system has a temperature T1 at state 1, or time 1 if you like. Okay? Now this mass is moving along and there is some friction. There's some friction going on here. Some friction going on between the moving eraser or mass, moving eraser or mass on the top of my table. So what's going to happen to that moving mass or eraser if I wait long enough in time? If I wait long enough, the mass is going to stop due to friction and come to rest. So I will get to state 2 if I wait long enough, in which the mass has moved and now stopped. So here's my table, and now my mass is over here. Okay? And it's stationary. So velocity, VEL2 is 0. Okay, the mass has stopped. Mass stops. Due to friction. Friction between the table and the mass has caused the mass to stop moving. Okay? So its final velocity is 0. Its initial velocity is not 0. It's VEL1. Okay? VEL1 is not 0. Greater than 0. Okay? VEL1 is greater than 0. All right? So I got my mass, I got my table at state 2. Okay? Let's apply the energy balance to my table mass system. I'm going to put a little control volume surrounding my table mass system. I'm just going to look at the table mass system. Okay? And I'm going to apply the energy balance. Which energy balance am I going to apply? Conservation of mechanical energy, just like you learned in basic physics. Okay, let's apply conservation of energy to our table mass or table eraser system. Let's see here. So work is equal to the change in kinetic energy from state 1 to state 2. 1, arrow 2, delta KE from state 1 to state 2, plus delta PE from state 1 to state 2. Okay? By the way, this should also be the work done on the system from state 1 to state 2. Okay, so far we're just doing a simple physics problem and applying conservation of mechanical energy. Okay? Now let's expand these terms here. The potential energy change, that's going to be PE2 minus PE1. That's what the delta PE1 to 2 refers to. The delta KE term, that's going to be KE2 minus KE1. That's our change in kinetic energy. Kinetic energy at state 2 minus kinetic energy at state 1. Okay? Now, let's start from the left. Let's start on the left-hand side and attack this equation and see what conservation of mechanical energy tells us about what's going on with